Uniform circular motion. Uniform circular motion is motion in a circle with constant speed. To figure out the speed of an object traveling in a circle, we can use the equation distance over time. Speed is equal to the distance divided by the time. What distance does an object travel in a circle? Well, that would be the circumference. How long does it take to travel once around the circle? Well, whatever that time is, it's called the period. That's the symbol for period. It's a T with two doohickeys. When an object travels in a circle, even at a constant speed, isn't its direction always changing? Therefore, we can say that its velocity is changing. Now recall that the definition of acceleration is the change in velocity divided by the time interval over which that change occurs. So if the velocity of this plane is changing, then shouldn't it be accelerating? Now, how can we figure out which way it's accelerating? Well, we could use a liquid accelerometer. Do you remember how the liquid accelerometer worked? Let's take a look.
Spin, the acceleration is directed inward. What we have is a centripetal acceleration.
So you can see that the liquid accelerometer points inward, meaning that there's an inward acceleration. Now, the equation for finding the acceleration, the centripetal acceleration, was derived by Christian Huygens. And he found it to be equal to the square of the speed divided by the radius of the circle that the object is traveling in. This reminds us that it's always center directed. The last lesson we saw that the centripetal acceleration was equal to the speed squared over the radius. So for example, if we have a car driving around a circular track of radius r at a speed v, this equation will give us its center-directed acceleration. If you remember, the liquid accelerometer shows that the acceleration is center-directed. From Newton's second law, sigma F equals ma, an acceleration is caused by a net force. The net force is always in the direction of the acceleration, so I'm going to call the net force that's causing the car to accelerate the centripetal force. So we have Fc then is equal to the mass of the car times its acceleration v squared over r. Now, the centripetal force isn't a new kind of force. It simply means a center-directed net force. Something has to provide it. The centripetal force is not a new kind of force. Something must always provide the centripetal force. In the case of a car rounding a corner, The centripetal force is provided by the force of static friction. If the force of static friction is a maximum value, that is, the car is on the verge of slipping, we can set this equal to the coefficient of static friction between the tire and the road times the normal force on the car. If it's a level surface that the car is driving on, then the normal force would be equal to the weight of the car where the weight of the car is equal to mass times the acceleration due to gravity. Solving for the speed of the car, we get that the speed of the car is equal to the square root of us, coefficient of static friction, times the radius of the curve, times the acceleration due to gravity. Let me draw a diagram. Here's the car, here's the center of the circle, the radius of the circle, r. Friction acts inward. If it's on the verge of slipping, it's a maximum force of static friction. The weight of the car acts downward, and the normal force acts upward. Consider an airplane flying in a circle. Notice that it's banked. The lift of the plane can be broken up into its x and y parts. The y part of the lift balances out the weight, and the x part of the lift provides the necessary centripetal force. The thrust balances out the drag if the plane is traveling in uniform circular motion. Here's the plane. Weight acts down. The lift force acts perpendicular to the wings. Break the lift force up into its x and y parts. It's the lift in the x that provides the necessary centripetal force for it to travel in a circle of radius r at constant speed v. This angle here, that angle there. You'll notice that this is very similar to the problem involving a car driving along a banked corner. Consider a satellite orbiting the Earth. Let's assume, for simplicity, that it's uniform circular motion. If we draw a free body diagram of the satellite, we see that the only force acting on it is the force of gravity. From Newton's universal law of gravitation, the force of gravity is equal to the universal constant times the mass of the satellite times the mass of the Earth divided by the center-to-center distance squared. The force of gravity is what provides the necessary center-directed force. So we have mv squared over r, the mass of the satellite times the speed of the satellite squared over the orbital radius of the satellite is equal to the gravitation constant times the mass of the satellite, which appears on this side too, so they get kicked out of town, times the mass of the Earth divided by the orbital radius. There was a ride at amusement parks which is sometimes called the rotor ride or the graviton. It's a cylindrical room, and riders experience the following force: the normal force, the force of friction and the weight. The force of friction keeps them from sliding down the wall, so this is a static friction force. And the normal force provides the necessary centripetal force. This they feel. They don't feel their weight. If the radius of the ride is r, then we can say that the normal force, which is the center-directed force, is equal to the mass of the rider times the speed of the rider squared. And at this moment, the rider is coming out of the board, divided by the radius of the cylinder. Now, the normal force can be related to the static friction force if the rider is on the verge of slipping downward. So let's make this the maximum force of static friction. So the normal force would be equal to the maximum force of static friction over the coefficient of static friction between the rider's back and the wall of the ride. But isn't the maximum force of static friction equal to the weight of the rider? Because the rider is in vertical equilibrium. The weight of the rider from Newton's second law is mg. So we have mg over mu s equals mv squared over r. The mass of the rider gets kicked out of town. So we're left with an expression. If we solve it for v, we get the square root of rg mu s. Excuse me. If we solve this expression for v, we get the square root of the radius of the ride times the acceleration due to gravity divided by the coefficient of static friction. Now, if this ride were at free fall, then we would have an apparent weight of 0. So it's as if there were no gravity. And then you can think of the only force acting on the rider as the normal force. This would create a simulated gravity. And if this room were large enough, this person might be able to get on their feet and walk around. This type of space station is featured in the motion picture 2001: A Space Odyssey by Stanley Kubrick. Vertical circular motion. Let's consider this plane that's in a dive and it pulls out of the dive. Let's consider the plane when it's right here. Okay, let's draw a free body diagram of the pilot. So when the pilot is at the bottom of the dive pulling out of it, what forces act on the pilot? Well, one of the forces, of course, is the pilot's weight. And the other force is the C, which is exerting an electric force upward on the pilot. We call this a support force or normal force. Notice that I drew that arrow longer than this arrow here. Why? Well, because don't we have to have a net force up so that the pilot can continue in the loop? Or else the pilot would follow a straight line path. And this causes an upward acceleration known as the centripetal acceleration. So if we use Newton's second law, sigma F equals ma, the net force is the center-directed force. That's equal to the mass of the pilot times the pilot's acceleration, which is center-directed, which we can write as v squared over r, where v is the speed of the pilot at the bottom of the loop, and r, of course, is the radius of the circular loop. The centripetal force then would be equal to the normal force minus the weight. The weight of the pilot would be mass of pilot times the acceleration due to gravity. This is what the pilot feels he or she weighs. This is the actual weight of the pilot. Now let's take a look at the top of a vertical loop. Okay, so the pilot would be in this position at the top of the loop. And let's draw a free body diagram of the pilot. You would have the weight of the pilot acting down, and you would have the seat exerting a downward force on the pilot. And that would be the normal force again. And these two forces added together give us the net force, or center-directed force. All right, so here is the outline of part of the vertical loop. Here's the radius of the loop. And these two forces together will cause the pilot to accelerate downward. Using Newton's second law, we would have that the net force is equal to the mass of the pilot times the pilot's acceleration. The net force is center-directed, so we could call it a centripetal force. That's equal to the mass of the pilot times the speed of the pilot squared divided by the radius of the loop. So here we would have, for net force, we would have normal force plus weight is equal to mv squared over r. Where again, normal force is what the pilot feels he or she weighs. Now it's possible for the plane to travel at such a speed that at the top of the loop, the pilot feels virtually weightless. So what would go to zero here is not the weight, but the normal force, because remember, that's what the pilot feels. So eliminating this, and then going over here, we eliminate this, we end up with mg is equal to mv squared over r. Notice the mass of the pilot appears on both sides. And what we could do here is solve for the speed, which is equal to the square root of rg. So that's the speed that the plane would have to travel at the top of the loop for the pilot to feel weightless.